Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in the last class of our discussion on induction machines, so particularly induction motor, so we have discussed torque slip characteristics and how say from input power to say output power has been developed, and from power flow diagram how we'll get the torque and how the torque slip are related, so that graphical representation was there, and finally we have discussed some numerical problems which will clear our understanding in that case. So hope you have enjoyed that discussions. Now today we'll discuss the induction motor equivalent circuit. You know, the induction motor is basically quite similar to transformer. So therefore induction motor equivalent circuit should also be similar to that of a transformer. So actually you have studied transformer in your last semesters, so it will not be very much say problematic for you to understand the induction motor equivalent circuit, because as it is more or less similar, or mostly similar, like transformer. But there is a basic difference. The only difference between them lies the fact that secondary winding, that is here in case of induction motor, the rotor rotates to give mechanical output, whereas transformer is a static device. So that's a very important difference. So the procedure and nature of induction motor equivalent circuit will be same as that of a transformer equivalent circuit. So to say draw the equivalent circuit or develop the equivalent circuit of induction motor, first of all we'll develop the circuit model of stator and then rotor individually, and after that we'll combine these two models to get the equivalent circuit of the induction motor. So let us start with the equivalent circuit of stator. Now what do we know? Actually, when a three-phase supply, power supply is provided, suppose the voltage is V1 is extended to the stator winding, rotating magnetic flux is developed in the air gap. So due to this rotating magnetic flux, a counter EMF equal to minus E1 is induced in all the three phases of the stator winding. So the now applied voltage, supply voltage is, if it is V1, must be balance this counter EMF as well as the voltage drop in the stator winding impedances. So if stator winding impedance is R1 plus jX1, where R1 is the resistance per phase of the stator winding and X1 is the reactance per phase of the stator winding, then I1 R1 plus jX1 will be the stator winding impedance drop. So we can write the supply voltage V1 should be equal to V1 prime plus I1 R1 plus jX1. The second part of this equation 1 is the stator winding impedance drop, and this is the counter EMF developed in the stator winding purpose. So that is V1 prime should be equal to minus E1, and I1 is the stator current. Now, as in case of a transformer, the stator current also consists of two components. One component is I2 dash, that is the load component. We have seen in the transformer operation like this here also, and counterbalances the negative rotor MMF, that is into dash I2 into prime actually. Another component is exciting current. The main purpose of this exciting current is to build the air gap flux and provide necessary load rotational losses of the induction motor. So mind the difference. So in case of transformer, exciting current, also called a no-load current, only builds the required flux in the core. But induction motors, apart from building air gap flux, it also provided the no-load rotational losses like windage loss and frictional loss. So this is very important. So exciting current transformers is not only build up the required flux in the core, but also it provide the rotational loss and frictional losses required for air gap flux. So it is provide this part also. So this exciting current IE, if I say it is IE, so it is again having two components. One is core loss component, that is IC, and another is a magnetizing current component, that is IM. So it is just similar to transformer. So the core loss component IC is in phase with voltage V1 prime, whereas the magnetizing component IM lags by 90 degree with V1 prime. So with in view of this discussion, the equivalent circuit model of the stator will be like this. So this is the supply voltage, stator winding per phase resistance, per phase reactance, and this is exciting current. This is the load component of the so this I1 is divided this plus this. So again exciting current is divided into two parts, that is core loss component current and the magnetizing component. So and this is the counter EMF in the stator winding. So that is actually E1, that is equal to should be minus E1 should be equal to V1 prime. So if we again discuss this portion like this, so IC and IM, as I told you, are connected in parallel, okay, and this is because IC is in phase with V1 prime, whereas IM lags 90 degree with V1 prime, and RC is taken as to account for the core loss in the induction motor, and XM is taken to account for the lagging behavior of the magnetizing component in the magnetizing current. So this is the stator circuit model which justify this equation 1. You know, if you go to the apply here this Kirchhoff's voltage law, you'll find so V1 equal to this plus this drop. Okay, so now we'll is it clear, no? I think you have understand it. So from this equation, how it is represented in here in the equivalent circuit. Okay, so now we'll come to the discussions of equivalent circuit of the rotor. Rotating air gap magnetic flux induced in the an EMF in the rotor circuit. We have discussed all this, and due to this induced EMF, current start flowing in the rotor bar conductors. That also we have discussed, which interacts with the rotating flux to develop a torque. Okay, and this rotor current and magnetic rotor current will generate rotating rotor flux, and that will interact with the air gap flux and to develop rotating develop torque. This is the very basic principle of operation of the induction motor, and due to this torque, the induction motor start rotating, and thus it is the induced EMF in the rotor which causes current to flow in the rotor winding. So this means the rotor EMF must supply for voltage drop in the rotor winding. So if we consider the standstill condition, the induced EMF in the rotor should be E2, whereas at full load slip it will be SE2. If S is the slip, then the voltage equation for rotor at full load slip will be this is induced EMF at slip S equal to, this is the say rotor current, and this is the rotor impedance at slip S. So this is the rotor resistance and it is the rotor reactance at slip S. So we can write this S I2 equal to SE2 by R2 plus JX2. Now if we say want to take it back into the supply frequency, then if we divide it is by S, so it will be E2 by R2 by S plus JX2. So there is a basic difference between these two equations, because so why this? Because though the current is same, but still there is one major technical difference, because equation 2 gives the value of the rotor current or load current at a slip S. So as rotor induced EMF is SE2. Okay. When the rotor winding resistance and reactance are R2 and X2 respectively here. And the equivalent circuit for this equation will be like this. Okay. This is the induced EMF. This is the rotor current. This is rotor resistance, and this is the rotor reactance. This is at supply slip frequency at a rotor. So rotor induced EMF. So this is the circuit model, and but equation 3, this equation gives the actually the rotor current when the induction motor is at standstill condition. Because at standstill condition S equal to 1. So therefore rotor induced EMF is E2 with rotor winding resistance and reactance will be in that case R2 by S and X2. So this equation 2 is correct as it gives the physical interpretation, but equation 3 is useful for getting the overall induction motor equivalent circuit. So the rotor equivalent circuit for this condition will be like this. This is E2, this is reactance, and this is the resistance. So of course this is at supply frequency X. So this is the rotor circuit model at standstill condition. Okay. So we developed this stator and the rotor equivalent circuit model. Now if we combine these two, then we'll get the complete induction motor equivalent circuit. So before we combining it, once again I am repeating this two circuit model. One is a quick recapitulation. This is the equivalent circuit stator circuit model. This is the basic equations of the supply voltage, induced EMF in the stator winding, and this is the impedance drop in the stator winding. And if we say put it in the circuit model like this, so this will be like this. And I told you it has stator current has two components. One is exciting current component, and it is this is the load component. This will be exciting current, again two component. One is the pole loss component, another is the magnetizing current component. And from this, if we say put it in a circuit model, so we'll get this stator circuit model like this. Now if you come to the equivalent circuit of the rotor, so this is the rotor induced EMF at slip frequency at slip, and this is the rotor loss at slip S. So you can modify this equation like this. This is for this we will develop this is the circuit model at slip frequency, and we modify this equation like this. It will be the this will help us to draw the rotor circuit model at standstill conditions, and this will be like this. So this is the induced EMF at standstill condition. This is the reactance, and this is your say rotor resistance at. So this is all about standstill supply frequency conditions. So I think this two circuit model is now clear to all of you. And next what we will do, So we'll combine this two circuit model, stator circuit model and rotor circuit model, to get the final equivalent circuit of the. So now we'll combine this stator circuit model and rotor circuit model to get the complete induction motor equivalent circuit. To combine this stator and rotor equivalent circuit, that is the stator circuit terminal voltage V1 prime and E2, that is the say rotor induced voltage at standstill constant, must be equal. But unfortunately E2 is not equal to V1 prime. So but we can transfer the E2 to the primary side, that is the stator side, by multiplying it by the turns ratio, as so we have done in case of transformer. So therefore the rotor terminal voltage E2 prime when referred to the stator side, so will be equal to how much? So it will be equal E2 into N1 prime by N2 prime, where N1 and N2 are the say turns ratio of number of turns of the stator winding and the rotor winding respectively. Say similarly, the rotor leakage impedance R2 by S plus JX2 and rotor current I2, that also must be transferred to the stator side, and these quantities when transferred to the stator side will be R2 dash by JX2 multiplied by N1 prime by N2 prime square will give you the R2 dash by S plus JX2 dash or X2 prime. So that is the impedance of the rotor impedance referred to the stator side, and I2 into N2 prime by N1 prime will give you equal to I2 prime, that is the rotor current say referred to the stator side. So these are two, and in that case the circuit will be like this. So this is E1 it is referred to the stator side. So this is your impedance reactance at the referred to the stator side, and this is resistance referred to the rotor side at supply frequency here. So this rotor parameters of the rotor equivalent circuit are corresponding to equation 3, that is earlier we have told. If we come here, this one, okay. So we refer to this equation 3, so we are able to get the transferred quantities at the stator of the rotor quantities. So this is because the stator circuit model and the circuit model corresponding to the rotor equation 3 are at the same line frequency F. Therefore, the frequency of the circuit model 2 for the equation 2 is SF, that is the slip frequency, and so it is not considered because the stator circuit model drawn at supply frequency and rotor circuit model has also been transferred to the stator side at supply frequency. So and then this will be like this, okay, and the corresponding quantities like transformers say being transferred with the help of the turns ratio when it is in the terms or in the case of say resistance, reactance or impedance, it will be multiplied by this ratio squared, and for resistance and say for current it will be multiplied by 1 by this turns ratio, that is N2 dash by N1 dash, like this. So now we are very well can combine these two stator circuit model and rotor circuit model because they are in the same frequency, okay, supply frequency. Now we combine. So this is this terminal AV of the stator as well as the rotor circuit now are the same, Therefore, they can combine to get the complete induction motor equivalent circuit. This will be like this. So this portion is stator circuit model at supply frequency, and this portion is the rotor circuit model again at the same supply frequency, because all the say rotor circuit parameters, that is resistance, current, voltage, reactance, all being transferred to the stator circuit at supply frequency. So now this can be, so this portion is common for both stator output and the rotor input. Okay. Now if we want to get a more generalized induction motor equivalent circuit, so we can omit this prime on R2 prime and X2 prime, and this will be like this. Okay, this will be like this. See the difference. Clear? So all primes has been removed. Okay. So this is your generalized equivalent circuit. Now another equivalent circuit may also be obtained by, if we split this resistance, rotor resistance, in this way, that is R2 by S equal to R2 is the same, R2 plus R2 into 1 minus S by S. So now this is split into two parts. So if we shown in the circuit equivalent circuit, this will be like this. See, this is R2, and this one this part, this one this part. Okay, but rest of all are the same. Rest portions are same. So let it become. Let it come. Okay, so that is, let's see. Yes, still it is not coming. Okay, we'll look that on. So this equivalent circuit shows the resemblance between an induction motor and the transformer, because you know at standstill condition, what is the value of the slip S? At standstill condition, rotor speed is 0. So slip will be how much? So it will be ns minus 0 by ns. So it will be 1 ns by ns. So therefore, at standstill condition, slip is 1. So R2 into 1 minus S by S, this portion. If it is 1, so what is the value of this portion? So this will be 0. Okay. So what does it mean? So this means the secondary is shorted. Okay. The secondary is shorted. So this is similar to that of a transformer equivalent circuit. And when the transformer secondary is shorted, let us see whether that figure has come or not. Yes, that has come. This has come. So see, actually what I was telling, this portion, it is divided into parts. These are two and this one. So this portion is divided into two parts, R2 and this part. Okay. So now come to the point here. So what I was telling, that is actually at standstill condition, slip is 1, and that means when S equal to 1, so this part is 0. This part 0 means secondary is shorted, like transformer. So it is the similar to that of a transformer equivalent circuit when the secondary is shorted. Again, when slip S equal to 0, S0 means what is the value of this portion? So this is infinity, because this is infinity. So this equivalent circuit becomes the same as open circuit transformer. Okay, so Like this, we can say the induction motor equivalent circuit, and R2 is the actual rotor winding resistance, whereas this is the electrical analog of the mechanical load. Clear? So this is very important. R2 is actually rotor winding resistance, and this is the electrical equivalent of mechanical load. So, you are finding the basic difference, since the transformer is a static device. There is no such case is arising out of the discussions. But since though both the equivalent circuit are similar, but basic difference is the rotor. Rotor is rotating, so induction motor having the rotor as a rotating part, and that's why equivalent circuit also must reflect that rotating part, and so that is taken care of here. This rotor resistance having divided into two parts, this R2 plus this one, and this R2 is the actual rotor resistance, and this part is the electrical analog of the mechanical load of which is for what the induction motor is being used. So that's all, and this will support our say logic, because if S equal to 1, that is at standstill condition, so this will behave like a short circuited rotor short circuit, that is the transformers secondary will be shorted like short circuit condition of the transformer. And when S equal to 0, that is switch 0, so this will be infinity, and this is similar to that of the open circuited condition of the transformer. So I think this will give you a clear picture about the equivalent circuit of the transformer, and once again I am telling you, to develop this equivalent circuit, we have taken the very resemblance of transformer, only with a basic difference that transformer is a static device, but induction motor is a rotating device, since its rotor is rotating. So to develop this complete say equivalent circuit of the induction motor, we have taken the help, like we have developed part by part. First of all, we have taken the help of the circuit model structure. We have first developed the stator circuit model, and this model has been developed from the very basic equations of the stator circuit, and then we have developed the rotor circuit model. So again, the rotor circuit model has been modified so after transferring it to the stator side to bring it in the same supply frequency, using just like a principle follow in case of transformer. And then we have discussed this circuit, complete circuit, and we have shown that how the rotor resistance has been divided into the two parts to show its rotor resistance as well as the electrical analog of the rotor circuit for mechanical load. Okay, so with this, I think we have ready to complete the equivalent circuit discussion of induction motor. So I hope everybody, all of you have understand this. You will, if you go step by step the development process of the induction motor equivalent circuit, starting keeping in mind the its resemblance with transformer, and with the little difference, since it is a rotating device, transformer is a static device. Then we have developed first stator circuit model, then rotor circuit model, Then we have combined these two. Before combining, we have taken the rotor circuit model into the same supply frequency. Then we have combined